High-voltage direct current HVDC is a modern transmission technology designed to move electric power over long distances using direct current DC instead of the more common alternating current AC. Unlike AC systems, which oscillate and experience reactive losses over distance, HVDC ensures minimal energy dissipation, precise control of power flow, and the ability to interconnect asynchronous grids. This makes it especially valuable for linking isolated generation sites, integrating renewable energy like offshore wind farms, and supporting cross-border energy trade. HVDC also requires less land and has narrower right-of-way requirements, making it ideal for congested or challenging terrains. The Monopolar HVDC system is the simplest and most cost-effective configuration of HVDC transmission. It employs a single high-voltage conductor typically operating at a negative polarity and uses the ground, C, or sometimes a dedicated metallic line as the return path for current. At each end of the transmission corridor, converter stations perform AC to DC conversion rectification and DC to AC conversion inversion, enabling seamless integration into conventional grids. One of its key advantages is reduced infrastructure cost, as only one conductor is needed for transmission. However, reliance on earth return introduces several challenges. Ground currents can lead to corrosion of underground metallic structures such as pipelines, interfere with communication networks, and affect the surrounding environment due to stray currents. Monopolar systems are often deployed in remote areas or as submarine links between islands and mainland grids. In modern practice, metallic return conductors are increasingly used to minimize environmental risks, despite the added cost and complexity. While fault tolerance is limited since any issue in the lone conductor interrupts transmission, the simplicity and economic viability of monopolar HVDC make it an appealing choice for low to moderate power transfers over extended distances. A monopolar HVDC system is a fundamental transmission configuration that employs a single high-voltage conductor, typically operating at negative polarity, with its return path flowing through the earth, C, or where environmental constraints demand a metallic return conductor. The converter stations positioned at each terminal generally utilize 6-pulse or 12-pulse converters to manage the rectification and inversion processes. For systems relying on earth return, dedicated electrode lines are installed, connecting to ground electrodes placed at considerable distances from converter stations, typically ranging from 15 to 55 kilometers, to minimize interference and ensure safe current dispersion. In cases where environmental preservation is paramount, a second conductor is introduced as a metallic return at medium voltage to eliminate direct ground current. Despite its simplicity and cost efficiency, the monopolar system is vulnerable to a single point of failure. Any fault in the transmission line disrupts power flow entirely. Moreover, ground currents can lead to serious issues such as pipeline corrosion, electromagnetic interference with communication systems, and broader environmental concerns. This topology is commonly seen in early HVDC deployments and in scenarios involving low-power cable transmission, and it often serves as the preliminary stage of a larger bipolar HVDC development. A bipolar HVDC system is a robust and widely adopted configuration for high-capacity, long-distance power transmission. It utilizes two conductors, one operating at a positive voltage and the other at an equal negative voltage, forming a symmetrical transmission link. At each converter station, the midpoint of the two poles is grounded through dedicated electrodes, which ensures that under normal operating conditions, the current remains balanced and no significant current flows through the earth. This grounding strategy enhances system stability and minimizes environmental impact. Each pole in a bipolar system is equipped with its own 12-pulse converter, allowing them to function independently. This modularity provides operational flexibility and fault resilience. For instance, if one pole experiences a fault or outage, the system can seamlessly transition into monopolar mode, using either a ground or metallic return path to maintain partial power transmission. This redundancy is a key advantage, ensuring continuity of service even during maintenance or unexpected failures. Voltage ratings for bipolar HVDC systems typically range from 500 kV to 800 kV, enabling the transfer of several gigawatts of power across vast distances. To support fault-tolerant operation, the system incorporates specialized protection mechanisms such as metallic return transfer breakers (MRTBs) and advanced switchgear. These components facilitate rapid switching between poles and return paths, safeguarding the system against disruptions. Bipolar HVDC links are commonly deployed in large-scale infrastructure projects, such as the Talcher Kolar Transmission Corridor in India, which connects remote generation sources to urban load centers. They are also instrumental in cross-border energy exchange and the integration of remote renewable resources like hydroelectric or solar power into national grids. Their ability to operate efficiently over thousands of kilometers makes them a cornerstone of modern energy networks. A homopolar HVDC system is a specialized configuration that employs two or more conductors, all operating at the same polarity, typically negative. This uniform polarity simplifies the insulation requirements across the transmission line, as the voltage stress is consistent and corona discharge is significantly reduced. The conductors in a homopolar system function in parallel, which allows for a more economical design by minimizing the cost of insulation and structural components. One of the notable operational characteristics of the homopolar system is its ability to maintain partial functionality in the event of a fault. If one conductor fails, the remaining conductors can continue to transmit power, albeit at a reduced capacity. However, this resilience comes at a cost. The system relies on the earth or sea as the return path for current, which introduces serious environmental and technical concerns. High ground currents can lead to corrosion of buried infrastructure such as pipelines, disrupt nearby communication systems through electromagnetic interference, and pose risks to ecological systems. Due to these drawbacks, homopolar HVDC systems are rarely implemented in modern power networks. Their limited fault tolerance, environmental impact, and incompatibility with contemporary grid standards have led engineers to favor bipolar or monopolar configurations with metallic return paths. Homopolar systems are now mostly of historical interest or used in niche applications where their simplicity might outweigh their limitations. A back-to-back HVDC system is a specialized configuration designed to interconnect two asynchronous AC power grids at a single location without the need for a transmission line between them. This setup is particularly useful when the two grids operate at different frequencies, phase angles, or standards, making direct AC coupling impractical. The system consists of two converters, a rectifier and an inverter housed within the same facility. The rectifier converts incoming AC power from one grid into DC, and the inverter immediately converts it back into AC for the second grid, enabling seamless energy exchange between otherwise incompatible systems. Technically, back-to-back HVDC systems operate at relatively low DC voltages, typically around 150 kV, but they are designed to handle high current levels to support substantial power transfer. Because the DC link is extremely short, the system does not require DC filters or ground electrodes, which simplifies the design and reduces the physical footprint.